I'll talk about smaller scale issues in lambda CDM, basically galaxy formation, what we can learn about galaxy formation and what lambda CDM predicts about galaxy formation on small scales. So we'll talk firstly about abundance matching, some of the so-called small-scale problems of lambda CDM, so abundance, missing satellites, too big to fail. I'll talk about measuring velocities directly, and again, I'll emphasise the role of feedback in galaxy formation. So we all have seen this, so I don't have to go through the initial conditions from the cosmology, from the UV background, N-body, so this is a pure N-body simulation with gravity. Okay, we see the structures forming. And one of the simplest things we can make, of course, is the halo mass function. And once we've got these final conditions, redshift 0, we run the simulation for redshift 0, and what we can do is just plot the mass on the x-axis and count the number of halos at each mass range. Okay? So this is divided by the volume, so within a given volume, how many halos do we have at each mass is the halo mass function. And of course, observers go out and they measure thousands or millions of galaxies, and we can do the same thing with their galaxies. We can see what the stellar mass of each galaxy is, and we can plot the stellar mass function of galaxies over here. Okay? So this is the stellar mass, and this is the number of galaxies. It's just counting galaxies, basically, in a given volume. And of course, Claudio showed this when we plot these two against each other, the halo mass function and the stellar mass function, they're very different shape. Okay, and this dotted line is the universal baryon fraction. So something's really changing the shape of this function. Okay, so what people normally do when they just want to match, cosmologists do, is just apply the widely invoked, poorly understood Frank principle, which is that the gold dark matter model and the observations are very different, so let's just assume that there's a physical process which has caused this stellar mass function to differ greatly from the halo mass function. And Claudio showed this plot. I think we Googled the same thing and found the same thing. This is put down to supernovae, and this is put down to AGM, but as I said, this is not well understood because this plot in some sense is wrong. These arrows are going the completely wrong way, so I made my own plot, okay? And what's happening is AGN is pushing in this direction along the x-axis to limit the number of stars that form. So we've got star mass on the x-axis here. So instead of getting the baryonic, universal baryonic fraction forming stars, at this mass range, we're getting a very small fraction of the baryons getting converted into stars. And this is attributed to the effects of AGN feedback, preventing star formation on these scales. On these smaller scales, as Claudio said, okay, the universal baryon fraction, only a small fraction getting converted to stars in halos in this mass range, and this is attributed to supernova feedback, the effect of supernova feedback.
Redshift 0?
This is at redshift 0. Yep. And then at the very smallest scales, and Claudia mentioned this is because, again, okay, UV background radiation is competing against cooling, and so in the very smallest mass halos, we think that the UV background radiation can prevent star formation as well. So let's just go ahead and assume that these processes are doing the job that we think they're doing, okay? Because this is the assumption, which means we can then match cold dark matter and the observed stellar mass function. And we can go ahead and do abundance matching. Okay? So what abundance matching means is we just draw these parallel lines, assuming these processes are working, and connect halos of this stellar mass, halos of this mass, to galaxies of this stellar mass. And so because this is a number function, this is a density, number density, if we just assume the same volume, then basically we're just rank ordering these things. So it just becomes a number. So we can just draw them the most massive halo at the top and the least massive halo at the bottom, and we can do the same thing for galaxies. And we assume that the top one matches the top one, the most massive, and we just go down the order. Okay, so that's abundance matching. So it's very simple. We just assume this. Okay? So, but really it's just making these assumptions that these processes, physical processes, are doing the job that we think they are. When we do this, we get this relation between the virial mass, the halo mass, and the stellar mass of the galaxies. Okay? And you can see it's quite a steep relation. Yeah, it's like this slope minus 2 or something. So, does this make any sense? This is the first question, of course. And we can actually go and measure halo masses in an independent way. So, using methods like X-rays, okay, weak lensing, satellite kinematics, we can get independent measures of the total mass, which includes the halo mass. And this is a plot, M halo, and these are measurements. This is from a Kravtsov compilation showing against the abundance matching relation. So it looks like this is working. Okay, so this is a big tick, of course, for LCDM. And of course, I won't talk more about the spatial distribution, because when you do abundance matching and you go and measure the 2-point correlation function, you get very similar results to what you get in n-body simulations. Okay, and Claudio again talked about, there's caveats about how you distribute things a little bit between the halos and baryonic effects. But I won't talk more about that. So what I will talk about first is this missing satellite problem. Okay? It's very easy. Right? Once we've done abundance matching. We just order the galaxies by their stellar mass. We order the halos by their halo mass. And what we find is we run out of galaxies. So that we've got all these halos with no galaxy associated with them. So at the low mass end, we've got all these extra halos. And that's the missing satellite problem. Okay, it originally came from it's called the missing satellite problem because it came from satellites around the Milky Way, because that's as far as we could observe at the low mass regime at that time, and it's what we were simulating. Okay, the first simulations showing excessive substructure within simulations compared to the local group, compared to the Milky Way satellite population. Right? But in fact, the missing satellite problem can be found on other scales in the local group. Or if you simulate the local group, for example, as Jenny was talking about yesterday, you've still got the missing satellite problem. We can now observe dwarf galaxies at larger scales. So it's in the field as well. So we've got missing small-scale dark matter halos do not have galaxies associated with them. That's the missing satellite problem. So one way we can resolve this is to try warm dark matter. So this has been explored quite a bit. Okay, so if you use warm dark matter, you're washing out the small-scale power, you're dampening the small power on small scales, and this is a cold dark matter simulation compared to 2 warm dark matter simulations, and you can see clearly the lessening of the small-scale structures here. And of course, you can do abundance matching with whatever cosmology you want, right? In warm dark matter, what can happen is you run out of small halos. Okay, so this puts constraints on how warm dark matter can be, because you need to create enough small-scale structures to account for all galaxies. So here we've got the halo mass function of different warm dark matter particles, entities. Right? So this puts constraints, and if you look at, for example, this Lovell et al. Paper, 2016, finds constraints of the warm dark matter must be above 5.5 kiloelectron volts to account for all of the dwarf galaxies that we see in the local region, in the local volume. One issue that I'll mention here, which sort of leads into Ariana's talk a little bit, is that warm dark matter sort of had this promise about it to solve the missing satellite problem and this cusp core problem at the same time. So people hoped that we could solve this problem here and then form dark matter halos with a much flatter inner density profile. Okay? But it turns out that once you put in this constraint, the warm dark matter makes NFW profiles, essentially. So you really can't solve both those problems with warm dark matter, which sort of lessens its appeal in that sense. Okay, so we can get more information about local dwarfs than just their stellar mass. We can actually go and measure their velocities. So this can give us an idea about the mass of the halo in which they live. Okay? So we don't just have their stellar mass. So once we go and do this, we get kinematic measurements of local dwarf galaxies. What we find is that those kinematics measurements seem to indicate that they live in actually these low mass halos down here, right? And what that means is that we've got these other high mass halos here, which do not have any galaxy associated with them. Right. So, I missed a slide. So, what I'll mention is, within this cold dark matter cosmology, the way to try and solve the missing satellite problem is to assume that these red galaxies here have not formed stars due to this UV background radiation, okay, that Claudia mentioned. So this UV background radiation is effective enough to prevent gas from cooling into those very low mass halos. So this is the solution that's proposed within a lambda cold dark matter scenario. Okay? But the problem is, it seems that these halos are hosting galaxies when we measure their kinematics, and then when we look at the abundance matching, it leaves these halos which are above the mass that we expect UV radiation to have any effect. So these green ones, we don't expect UV radiation to be preventing star formation. And yet, when we measure kinematics, those galaxies, those halos are not hosting galaxies. Okay? And this is how the too big to fail problem is often plotted. So these are the local group dwarf galaxies in white, and these are the Milky Way satellite halos from a simulation. And you can see there's all these halos that don't seem to host any dwarf galaxy. They're more massive than you would expect UV radiation to have an effect, and so we call them too big to fail. They don't seem to be hosting galaxies. Another mismatch between cosmology and observed galaxies, once we start measuring velocities, comes in the form of the velocity function. So again, the velocity function is very related to the mass function in n-body simulations. Okay, so the maximum velocity is very close to its mass. There's just a caveat of the concentration, right? But here's the mass function, the velocity function of n-body simulations is this dashed line. If we go and measure the maximum velocity, circular velocity of a whole large sample of galaxies using H1 circular velocities, we get this white population here. Okay? At the high mass end, this can be explained by adiabatic contraction, okay, which is what Claudio said again. It's the cooling of the gas to the centre of the halo, pulling in the dark matter and making it more dense in the central region, increasing the velocity, and we can explain this high mass end, but there's a big discrepancy down here at the low mass end again. And this might be related to this cusp core problem, which Ariana will talk a lot about, okay, which is the predictions of a lambda cold dark matter is this red line, and when we, for the velocity versus radius, which comes from just using the density versus radius from an n-body simulation, and using GM over R to calculate the velocity. But when we observe galaxies, of course, the rotation curves have a very different shape to what's predicted from pure n-body simulations. So Ariana will talk about that. And in fact, this too big to fail problem could be just related to the cusp core problem. Because when we measure these velocity dispersions, okay, we infer that they're in low mass halos, but in fact they might be in chord halos. And the chord halo might be resulting in the low velocity dispersions rather than the low mass halo. Okay, so there's a degeneracy here. If we have dark matter cores, then we can solve the too big to fail problem. Okay, if we do abundance matching, there's also problems. If we use the predictions of the velocities coming from pure n-body simulations, again, the Tully-Fisher relation, which is the stellar mass versus the rotational velocity, and we don't really get a good match. Again, the effects of baryons really need to be included in the modelling before we can make these detailed comparisons between predictions and galaxy populations. So we really are trying to ask, when we make these models like Claudia was talking about with hydrodynamic simulations, is can these problems and a whole multitude of galaxy formation, of galaxy observations, such as the CGM or where the metals are found, or the metallicity of galaxies, okay, relations between metallicity and mass. There's a whole bunch of observations out there, and we want to self-consistently solve all of them within a cold dark matter paradigm. So if we break one, if we improve, or if we match one set of observations, does this self-consistently allow us to match another set of observations? And there's many independent observations, and the goal is to try and self-consistently match all of them. I think early on the simulations were able to often match one set of simulations and then not show in the paper that they missed a whole bunch of other relations. But now we're getting much better. So what we do to try and model the really detailed part of galaxy formation, the details of a single galaxy, as Claudio mentioned, is we do these zoom simulations, which is to just run a full box of n-body, find a halo that we're interested in. It might be like a Milky Way analogue, might be a local group analogue, might be a dwarf galaxy. Okay, we identify it in the final z=0 n-body simulation. We trace those particles back and find where they were initially, and then just in this volume here, that's where we model all these processes that Claudio talked about. So we don't model gas cooling and star formation in the whole box, we just model it in this one little region here. And that allows us to get higher resolution because we're not modelling all these processes throughout the whole box. Right, so then we include gas dynamics, as Claudio said, UV background radiation, cooling, okay, star formation, importantly feedback from stars and from supernovae. Okay, all these things go into the codes, as Claudio said, and we trace the evolution of all these different metals. Okay, so we can make comparisons between other types of observations as well. So we trace their formation in stars and how they get spread through the universe. Okay, and really it's quite astonishing how far we've come in the last few years. This is one of Phil Hopkins' simulations of a Milky Way. Okay, so this is a full hydro simulation of the Milky Way, and you can see all the detailed structure that now can be formed within these zoom-in simulations. Right? So we're not just doing global properties, we're looking at really detailed structure of galaxies being formed within a fully cosmological context, including many processes of galaxy formation. So when people started doing this, they weren't very successful. Okay, the gas was cooling too far into the centre of the galaxies. So what I've plotted here is these are simulations, and this is the angular momentum of the simulations versus observed galaxies. Right? Basically, the simulations were losing a lot of angular momentum. The gas was cooling to the centre, forming stars, and mergers were happening. The angular momentum was getting transferred from these stars to the dark matter halo, and you ended up with big spheroids, basically, rather than nice disks. Another problem that's persisted until recently with these simulations has been that they're forming too many stars. So the solution to both of these problems and a multitude of other problems with galaxy formation simulations has just been the way we do feedback. And essentially we really need to put in, couple the energy that's available to us from supernovae and AGN quite strongly to the gas. It has to be really effective. Okay? So what we do in these simulations, what we often do is tune our feedback parameters, or the coupling of our feedback to the gas, in order to get the correct number of stars. So Claudio said, okay, we now match the luminosity function. So this is the same thing. We're matching in smallest zoom simulations, what we try and match is this relation between M halo and M star. Okay? So we try and get the correct amount of stars for a given halo mass, because otherwise LCDM is not working at all, because we're going to have the completely wrong number of stars. So this is how we tune our feedback parameters, because there's some uncertainty in the, let's say, in the feedback. Okay? It's not extremely well modeled. But what we find is, once we put in enough feedback to get the correct number of stars, a whole bunch of other observed galaxy relations just kind of fell out of the simulations. Okay? So here, again, we've got M star M halo, and we've got a series of a few simulations here. This is actually an old simulation showing what happens when you form too many stars and you don't have effective feedback. You form too many stars and you end up here, and you miss this relation. So all we did was really tune our feedback to keep one of these stars, one of these correct number of stars in one of these halos. And what you find is, by keeping the same physical processes, you can actually, in all of these galaxies, you can actually match the M star M halo relation, which in itself is saying something, okay, because the amount of energy that we're putting in is related to the star formation. And so we get the correct relation just by putting in this amount of energy. You've got stars fighting against dark matter potentials, right? So as you get lower and lower dark matter potential, you need a certain amount of energy to prevent star formation. And this amount of energy was scaling in the correct way, right? But to give us the correct stellar mass halo mass relation, which is a non-trivial sort of relation. So that's already encouraging. But what we found is, once we did this, a whole bunch of other relations, observed relations, started to get more or less the correct results. So, for example, the Tully-Fisher relation, which is the rotational velocity versus the luminosity, basically the stellar mass. Okay, so we're getting more or less the right rotational velocity. The baryonic Tully-Fisher relation, so we're plotting cold gas plus stars on the y-axis here versus the rotational velocity rather than just stars. So we're getting the correct amount of cold gas as well, more or less. The specific star formation rate, okay, so how many stars are the galaxies forming at redshift 0 compared to their stellar mass. The size, as Claudio said, okay, another constraint on these models. So what's the half-life radius of these galaxies compared to the rotational velocity, for example. And also relations relating to their metallicity. Okay, so we're getting more or less the correct amount of metals in the galaxies compared to their stellar mass. So this has really moved this field a long way forward in the last just several years, I guess. So similar to how Claudio was saying, the large-scale simulations have really come a long way. Same with these zoom-in simulations. Okay? And another way, and Claudio again mentioned this, all right? So we also have to match the metals that are surrounding galaxies. So in order to get the correct metals in the surrounding region, in the outer regions of galaxies, we also need similar feedback processes. Okay? And so if you put in the amount of feedback in order to get the correct stellar mass in a galaxy, you start to match the metals in the surrounding CGM, and this is another great constraint for our simulations. Whereas if you put the feedback where you get too many stars forming, there's not enough effect from the feedback, then you're also not pushing the metals to large enough radii, and you've completely failed to match any of these observations. Okay. And then I won't go into the detail of this, but when we start getting these results, we can start to create models that include baryons, that start to, plausible models that start to match these velocity functions. So this number of, these counts of galaxies by measuring their rotational velocities. Right? And so there's a big difference between cold dark matter Vmax, using cold dark matter only simulations, and the measured internal velocities of galaxies that you expect when you do a full simulation and you include baryonic processes and you model baryons in a self-consistent way. So I'll just conclude here. When comparing CDM models with observations, it's really, of galaxies, I guess I should write that, it's imperative to model baryons. So very careful comparisons are required. And so it's not only modelling the baryons, but it's using techniques which really try and mimic what the observers are seeing, rather than just using, okay, here's Vmax from a simulation, here's the maximum circular velocity, let's compare that to what the observers are doing. But we have to be clear, are the observers really measuring Vmax of the halo, or are they measuring something a little bit different? So we have to be very careful the way we do all sorts of comparisons. But once we have become better and better at this, it seems that CDM may be able to self-consistently explain a range of observed galaxy properties, and I think I'm not the first person to say that it's annoyingly good match of CDM to some of these observations. Okay, this week we've seen a lot of things that sort of people would like to see a deviation from CDM, but it seems to be doing quite a good job within forming galaxies on small scales. There's certainly, I would say there's no unambiguous contradiction between galaxy properties and the CDM paradigm at the moment. Other people would disagree with me. There's certainly people in the community who would point to some galaxy properties and say this is not consistent with CDM. I personally think that there's no unambiguous contradiction, but tensions do persist, and key processes such as the way these supernovae and AGN feedback actually are modelled, and our understanding of them and our observations of them, okay, these are still really quite poorly understood and quite crudely modelled. So there's a lot of work to be done and understanding to be gained about these processes that we really rely on heavily. And I'll finish there.